Consider the forces acting on an evacuated vessel. Atmospheric air pressure on the outside is pushing inwards in all directions, and inside, many fewer molecules are pushing back out, and that means there is a net force inwards. The first person to realize the potential of this was called Otto Von Guericke. In 1650s Germany, he realized that by removing the gas from the space between two hemispheres, the net forces of the surrounding air pressure would hold those two hemispheres together. Von Guericke was a famous politician, a scientist and a showman, and in 1654 he staged an extravagant demonstration in the city of Magdeburg. Spectators lined the street to see that even a team of horses couldn't separate the two hemispheres. We could use a small vacuum pump to recreate the experiment, but actually we don't need to go to the trouble. We can use these plungers to recreate what Magdeburg did. So I'll do it once, and then I'll talk through what's going on at each step. So when we start, we match up these two hemispheres so that they meet in the center, and the air inside and the air outside is still atmospheric pressure. So step one is to pump out some of the air. And when I squeeze them together, they're acting like a diaphragm. You can hear the air escape. The volume between the handles is now smaller, but the pressure inside is still atmospheric. So the next thing is to separate the two handles, pull them apart a little, and that increases the size of the chamber. And when I do that, the molecules inside need to spread out to fill the space, and as a result, the pressure of the chamber drops. The air pressure on the outside is still pushing them together, and the rubber seal on each plunger stops any air leaking back in, so suddenly the plungers are stuck together. It took a little effort to pull those two hemispheres apart because we'd pumped out some of the gas and we had to work against atmospheric pressure. Atmosphere on the surface is roughly 1 kilogram per centimetre squared of surface area. So if we could ever achieve a perfect vacuum in a suction cup, we'd be able to lift 10 tons for every metre squared surface area of the cup. That effect, which von Guericke first understood 400 years ago, is now put to use everywhere. When you see a sat-nav hanging to the window of a car, glass windows being lifted by suction cups, or toy darts sticking to a target, the same principle is going on. The air is pumped out, a seal stops air leaking back in, and air pressure from atmosphere pushes from the outside to hold the sucker in place. And this leads us to maybe the most common use of vacuum equipment today, pick and place. Options for holding and lifting during production are really limited to magnetic, mechanical clamping, or vacuum suction cups. And when a product is not magnetic and is too delicate or oddly shaped to be clamped, then vacuum provides the perfect solution. If the product being lifted is light, and if the contact area with the sucker is a nice smooth surface, and the equipment has a well-maintained rubber seal, then we can rely on such a low leak rate that the vacuum sucker will hold. But more often than not, in industrial pick and place, a good seal is not guaranteed or even likely. Take paper processing. It's impossible to create a leak-tight seal because air can bleed directly through the paper. So we need to constantly pump out the leaks to maintain a low pressure at the workpiece and therefore maintain a reliable lifting capacity at the point of use.